So hello everyone, welcome back to another particular lecture of our reagent chemistry course, and this is the class 19. And in the previous discussion, we are talking about the epoxidation by using MCPBA and other per acid based reagents. So today we are talking about the epoxidation of double bonds, especially the nucleophilic and epoxidating agents. So initially we began with our discussion with the Br2 NaOH based epoxidation. So Br2 NaOH based epoxidation is reagent, sometimes written as NBS NaOH. Basically, a bromine source is required and a base is required to do this type of epoxidation. And it is a two-step reaction to generate the epoxide ring that will be discussed in the mechanistic pathway. And the very important thing is, this particular reaction is famous for the synthesis of epoxide on the more hindered side. So as I already discussed in the MCPBA based case, that the epoxide is generated from the less hindered side. But in the case of this particular reaction condition, Br2 NaOH, this particular epoxide is generated the more hindered side. So this is the very key distinguishing feature between the Br2 NaOH and MCPBA based epoxidating agents. And this particular reaction typically involves the formation of a bromohydrin ring and then followed by intermolecular nucleophilic substitution. So let us understand the mechanism first and then we'll discuss later further. So first, the mechanism of Br2 NaOH mediated epoxidation, that initially that bromine are actually breaks by this particular base and it will generate HOBr or NaOBr. Okay, so what happened then? This particular bromine is break. So this particular Br plus will actually captured by this particular electron-rich olefin, and it will generate this particular three-member intermediate. Then the OH minus present there, this will actually attacks from the SN2 pathway here, and it will be generate the bromohydrin intermediate. And after that, in presence of base, this particular proton has been captured. So this particular negative charge will show a intermolecular SN2 pathway to kick out this particular bromine, and we got our this particular epoxide ring. So initially the bromine three-member ring stereochemistry is above the plane, and the resulting final epoxide stereochemistry is below the plane. And this is the actually the key feature, and that's why the particular product is generated in the more hindered side. So let us give a simple comparison between this Br2 NaOH mediated epoxidation and the MCPBA mediated epoxidation. So here it is written that Br2 NaOH shows more hindered side epoxidation, whereas the MCPBA yield less hindered side epoxidation. Like this particular compound is there, in presence of MCPBA, the epoxidation stereochemistry is something like this, whereas this particular Br2 NaOH based epoxidation stereochemistry looks like this. This is because that initially bromine is actually attached here in the less hindered side, but after that, since SN2 type of reaction has been observed, that's why the stereochemistry getting reversed, and for that particular reason, this particular product becomes the major product. For the similar reaction here, this is the bulky group present here. So in presence of MCPBA, the lower side epoxidation takes place to avoid the steric repulsion. However, in the case of Br2 NaOH, the same side epoxidation has been observed because of the reaction mechanism that I already discussed. Now let us talk about another nucleophilic epoxidizing agent. This is the hydrogen peroxide. So hydrogen peroxide is an environmentally friendly oxidant producing water as the only byproduct in epoxidation reactions. And this particular H2O2 based epoxidation is usually not stereospecific, often used with catalysis like transition metal or organocatalyst to improve the selectivity and efficiency. It will do the epoxidation, but this is not a stereospecific reaction. Earlier, like MCPBA and Br2 NaOH, those are the stereospecific, but this is the not stereospecific reaction. And also it will react with the electron deficient alkanes, especially alpha beta unsaturated carbonyl compounds. So if you have this type of alpha beta unsaturated carbonyl compound, and if you want to do epoxidation on this particular double bond, then you can use H2O2 and OH, and the reaction mechanism is something like this. This O negative attack in here, and this particular bond goes up, and then this goes down, and this will attack in this particular electron deficient oxygen, and which kicks out this particular OH, and finally we got this type of epoxide. Now let us talk about another type of epoxidation. That is a sulfur ylide mediated epoxidizing agent. Now sulfur ylide have numerous application in organic synthesis because it is actually good C1 synthon in the case of sulfur ylide. Now among them there is a two different sulfonium ylides is there. One is the sulfonium ylide, and one is the sulfooxonium ylide. Now sulfonium ylides are an unstable ylide, and it will generate the hard nucleophile. But in the case of sulfooxonium ylide, it is stable ylide, and it is actually do the soft nucleophile. And due to the different nucleophilicity, this will show different reactions. For example, if you have this type of alpha beta unsaturated carbonyl compound, now in presence of sulfonium ylide, since it is unstable, that's why it is a hard nucleophile, and since it is a hard nucleophile, then it will show 1,2 attack, and after 1,2 attack, then you will generate the epoxide from here, like 1 carbon is increased in that particular case. Like it is written here that hard nucleophile 1,2 addition, 1 carbon homologation takes place, and double bond keeping untouched here. And in the case, by treating this same alpha beta unsaturated carbonyl compound with sulfooxonium ylide, which is stable and soft nucleophile, then it will show cyclopropanation reaction. And this particular reaction is called Korey-Chablowski reaction. And here the carbonyl group getting untouched. So if you have a alpha beta unsaturated carbonyl compound, and if you want to do 1,2 epoxidation like this type of compound, then you can use the sulfonium ylide. And if you want to generate a epoxide in this particular double bond, then you can use H2O2. So thus you can do the epoxidation. So with this, we have to end all the discussion regarding epoxidation. So from the next class onwards, we talk about the dihydroxylation of double bond. So thank you for listening.